Thanks, sir.
You're welcome.
All right. So again, we're not going to do many slides today. Please return those stethoscopes back to the box and return to your seats. Kristen, Hayden, please return the box.
You're supposed to get all of them.
What?
There's a lot of rainbow colors.
I got them. Yeah, I don't know.
All right. So again, I'm only going to do a few slides here, and then we'll be done. No homework this weekend. When it comes to Monday and Tuesday, keep an eye out because I won't see you until Wednesday. Just keep an eye out on Classroom, see if there's anything that gets posted. But we are still undecided if we're going to put the second half of the notes out on Monday or not. Again, just stay tuned, and we'll let you know. But we are going to talk about a gentleman by the name of Niels Bohr. Now, Niels Bohr and Albert Einstein got along but didn't get along. They had a lot of competing views on why things were the way they were. Bohr, that is, correctly predicted the frequency lines in hydrogen's atomic emission spectrum. Okay, we had helium, we didn't have hydrogen, but he was able to do this. And he's able to predict it to be discontinuous like you saw with those other gases today. And so when you have electrons, and we're talking about hydrogen right now, you have what's called a ground state and an excited state. The ground state is what it sounds like. It's the lowest allowable energy state an atom can have. So like in the basement, okay, the ground. Then you have the excited state when you have atoms gaining energy. And you just witnessed that with those gas tubes. Hydrogen is capable of having many different excited states, even though it only has a single electron. It is all dependent on how much energy it absorbs. Bohr suggested that a single electron in a hydrogen atom can move around the nucleus only in certain allowed circular orbits. Smaller the electron orbit, the lower the energy. The larger the electron's orbit, the higher the energy. And so what Bohr did, he assigned what we called early quantum numbers to these energy states. Essentially, each orbit that an electron went into was a different quantum number. So we do touch base a little bit on quantum mechanics in here. So Bohr wanted to explain what the line spectra of hydrogen was doing. He said each orbit was given a number. He called it the quantum number, which is represented by the lowercase n. So anytime you see a lowercase n, that's typically going to mean the energy level that an electron could be or is. And so hydrogen's single electron, when in the ground state, is at n equals 1. So the first energy level number 1, is considered the ground state. When we add energy, that electron is going to absorb the energy, then it's going to move into a higher energy orbit, which could be n equals 2 or n equals 3, which means energy level 2, energy level 3, okay? But the electron can also drop from the higher energy orbits to lower energy orbits. And by doing so, it's going to emit a photon corresponding to the difference between the energy levels associated with those two orbits. So each of these energy levels has a certain amount of energy required to get to that level. But only certain atomic energies are possible. It only allows for certain frequencies of electromagnetic radiation to be emitted. The hydrogen atom's electron can move only from one allowable orbit into another. And so it can emit, it can absorb only these certain amounts. It has, think of a stair step. Okay? You're either on a step, as you walk up and down the stairs, you're either on a step or below a step, okay? But you're always on a step. You never step in between a set of steps and hope that you can go up. You can only be on a step, nowhere in between. Those steps are equivalent to these energy levels. Okay? You can exist on a step, and each step is going to have a varying amount of energy that is required to exist there, but you cannot exist between steps. Even though Bohr's idea of using the hydrogen atom was correct, anything beyond a hydrogen atom, which we know is a significant amount of elements, didn't explain everything. It cannot explain any other elements' spectral lines. In the poster underneath the sloth over by Mr. Workman, it shows elemental spectral lines for each element. So we had a lot to learn after Bohr, because he only did the very first one. Bohr's model also did not fully account for the chemical behavior of atoms. But the behavior of electrons is still not fully known. Known electrons do not move around the nucleus in circular orbits. So our previous model, where we had electrons looking like planets going about the nucleus that resembled the sun, so like the solar system model, that is no longer the correct model that we use. We use probability. We use math, calculus, in order to predict where we should expect an electron to exist based upon its electron orientation, configuration, and the energy with it. We're going to stop there.